Hi, how's everyone still feeling? Okay. So we were just talking about how the friction force depends on how much the two solids are being squeezed together. And the normal force is always a measure of that. So let's go and take a look at a video here. How much was the friction force in the initial one when I pulled in the video there? 14 newtons. So this time I stacked another brick on top of it. We increased the amount that the brick is being squeezed into the board. Right now I'm pulling with an applied force of 18 newtons. So the static friction force holding it there is 18 newtons. Pulling with 20 newtons. So the static friction holding it there is 20 newtons. How high will it go this time before it budges? And it went about 22 newtons there. If it was working perfectly, guess what I hoped it would have gone to? 28 newtons, because I doubled the weight there. I put another brick on top. So, you know, if things were working perfectly there, maybe that top brick didn't weigh as much as the bottom brick. But for whatever reason. But obviously, when you squeeze the two surfaces together more, there's more of a grip. There's a bigger friction force holding it back. So, let's go back to the PowerPoint. So, one factor that affects the friction force is the amount that the two surfaces are squeezed together. Okay, so the other factor that affects the friction force is the texture of the two surfaces that are in contact with each other. Whether they're like slippery or grippy. Whether they're smooth or they have a bunch of nooks and crannies. The texture of the two surfaces that are rubbing up against each other has a huge influence on the friction force. So it's kind of interesting. Physicists have actually rated the combinations of surfaces in contact with each other and given each combination a number rating to indicate how slippery or grippy the material is. So the friction force is directly proportional to the texture rating, the texture of the two objects that are in contact with each other. And the way this rating goes, it's usually between 0 and 1. And the texture number is a 0 if it's super slippery, like no friction. And it's closer to the number 1 when it's, you know, it's got a lot of grip. For lack of a better word, I'm going to say grippy. Most of the time, the texture number is between 0 and 1, but sometimes it's so grippy, it's actually greater than 1. But usually it's just between 0 and 1. Now, this texture number has an official name. It's called the coefficient of friction. So the friction force, which is the thing that we're trying to calculate, the friction force, you know, how much actually holds it back, is directly proportional to, there's that little symbol, directly proportional to the texture number, but the official name of the texture number is the coefficient of friction. coefficient of friction is the Greek symbol mu. So it looks kind of like a U. There's a U like that. But do you see how the U has like a little tail on this side? Well, the mu has the same thing on both sides, but then some people think it looks like an M, but it's not. It's a U with a little tail on both sides. It's also the micro symbol in the metric system, and it stands for 10 to the negative 6, or a millionth. But here, this is the symbol mu. So we could say that the friction force is directly proportional to the texture number, mu, of the two surfaces in contact with each other. Now, on the Regents reference table, you're given a chart of all the mu's, of all the coefficients of friction. But another interesting thing you see from the chart, the mu changes depending on whether it's static, still, or kinetic, sliding. So for example, like rubber tire on dry asphalt, like a dry road, the static friction force has a mu of 0.85. Whoops. But the mu for the kinetic friction is 0.67. Every time I touch it, it goes back. Sorry about that.
Why do some of them not have static friction values?
This particular chart just doesn't have those values, so that sometimes the students have to calculate those values. It's not that they're not known. Very good question.
5, that's outstanding. Skis.
Okay, so in summary, the friction force depends on two things: how much the two surfaces are being squeezed together, and the texture of the two surfaces. How much the two surfaces are being squeezed together can be represented by the normal force, and the texture of the two surfaces is represented by the coefficient of friction. So we're going to take these two factors and make it more mathematical, make it a formula. So the bottom line is, folks, if you turn this into a formula, it looks something like this. The force of friction equals the normal force times the coefficient of friction. So you could see the two factors there that affect the friction force. It's tricky because on the left you have F sub F, the force of friction. On the right you have mu, which is the coefficient of friction. And they kind of sound similar. Force of friction, coefficient of friction. But what you need to remember is the coefficient of friction, the mu, that is just one factor that affects the friction force. Whoa, my little diagram here is out of whack there. All right. And it didn't get changed properly, but usually it's written force of friction equals mu times the normal force.
Does it matter?
It doesn't really matter, but that's just more common. So, we need to clarify something. Even though it seems as if there's just one friction formula, the friction force is equal to mu, the texture number, times the normal force. We have to remember there's two types of friction forces. There is a static friction force and there is a kinetic friction force. So there's really two versions of this formula. Now, the version for the kinetic friction force is straightforward. It basically looks like this. The force of friction, F sub F, and then I actually write it with another subscript, sub K. The force of friction, kinetic, is equal to the coefficient of kinetic friction, which is denoted mu sub K, the texture number when it's sliding, times the normal force. How much the two objects are being squeezed together. Now, the static friction force, it's more complicated. Because remember, the static friction force varies between 0 and up to some maximum value. So there's two ways of stating the static friction formula. You could state it like this. You could say that, look, if you want to calculate the maximum static friction force, I get carried away with subscripts. F sub S sub max. The maximum static friction force. The biggest static friction force you can have right before it budges. That is always equal to mu sub S, the texture number when it's still, times the normal force, but here's the thing. That's just the maximum static friction force. If you just wanted to say in general, the static friction force, you can't just put an equal sign in there if you want to say mu sub S times the normal. Because mu sub S times the normal always gives you the maximum. You know, that always gives you the maximum. So, but remember, the actual static friction force might be less than the maximum. If you're only pushing on it with 1 Newton and it's holding, then the friction force is only 1 Newton. So what symbol would I put in there? I think I heard someone say it.
John, you said it too.
Less than.
It's less than or equal to.
Oh, that's how it's done.
Is there a way to derive these formulas or just
No, it's just like experimentally found.
okay, it's just because
It's fundamental.
indeed.
So we go back to the PowerPoint here. Take a moment and see if you can figure out, you know, parts A, B, and C here. You have a 5-kilogram brick set on a table, and you're given the two texture numbers. Mu sub S is 0.5, mu sub K is 0.4. And the first question is, look,
What is the normal?
if you're going to push on that brick, part A, and get it to budge, how much would you have to push on it to get it to just barely budge? So take a moment and see if you can calculate that out.
Oh, the fact that I know how to do this right now makes me very happy.
we're trying to find FFK.
Well, to get the brick to start sliding, what are you going to have to overcome first?
The maximum static.
The maximum static friction force.
Yes.
To get it to start sliding,
I love this unit.
you have to push with just a smidge more than the maximum static friction force.
There's no unit for coefficient of friction?
There's no units for coefficient of friction.
Why
It's
do you-
just a number that represents the slipperiness. Okay, I'm going to go to the Mimeo so I could write this up here.
What was the?
What was the second question?
Let me see first. Oh, the 5 kg brick is F normal. The normal force is the weight of the brick.
All right, so if the mass of the brick was 5 kilograms, the weight of the brick is going to be 5 times 10 meters per second squared. Which is going to equal 50 newtons.
Why 10 meters per second squared?
Remember, when you're converting between mass and weight,
Oh, okay. So
you could imagine that the object is in free fall, and if it was in free fall, the only force acting on it would be its weight force, and the acceleration due to gravity would be 10 meters per second squared.
Okay.
Now, in this case here, the table or whatever beneath it is holding it up, which is really acting like here, holding it up, but normally we don't draw it there. We draw the normal force up this way. And in that case, it's going to be equal to the weight force, 50 newtons. Now, if you pull on that object with a certain applied force, there's going to be a rubbing friction force that acts in the opposite direction. And at first it's going to be a static friction force. And if you pull with 2 newtons, the static friction force would be 2 newtons. And if you pull with 3 newtons, the static friction force would be 3 newtons. But we're trying to figure out how much would you have to pull to get it to budge. Well, in order to figure that out, we need to go and calculate the maximum static friction force. But we could do that with the formula mu sub s times the normal force, because the friction force depends on 2 things: the texture number and how much the two are being squeezed together, the normal force. So in this case, it's 0.50 times the normal force, which is 50 newtons. So what's that going to be? 25 newtons. So most people will just put the answer of 25 newtons for part A, but technically, and you get full credit if you just say 25 newtons, but technically, what really is it?
Greater than 25 newtons.
A smidge more than 25 newtons. 25.000001 newtons will get it to budge. But people will just say 25 newtons. But really, 25 newtons is the biggest static friction force that will just hold it. And you'd have to push it with just a smidge more.
But don't we round in this class?
But nonetheless, that's why we could just leave it 25 newtons.
Go rounding.
So, if they ask you how much does it take to start the object, then you're going to calculate the maximum maximum static friction force. But then in part B, they said, all right, look, now you got it sliding. How much force would you have to keep applying to keep it going at a constant velocity? So this is your answer to part A. For part B, we need to calculate the sliding friction force, the friction force kinetic. Well, remember, the friction force always depends on two factors. The texture number, officially called the coefficient of friction, but in this case, it's the kinetic coefficient, and the normal force, how much the two objects are being squeezed together. So the force of friction, kinetic, is going to equal, what was it, 0.3?
0.4.
0.4? Just a number, usually between 0 and 1, indicates the slipperiness or the grippiness of the texture, times the normal force.
10
But what's the normal force still?
25 newtons.
No.
Oh, sorry, 50 newtons.
50 newtons. So, once you get it to start sliding, how much friction force is there? 0.4 times 50? Is it 20?
Yeah.
Yeah.
Now, if you want this object to be moving forward at a constant velocity, and we know that the kinetic friction force, K, is 20 newtons, how much would you have to pull forward to keep it going forward at a constant velocity?
20 newtons.
20 newtons. So, how much would you have to keep it going? 20 newtons. So when you see that word keep, to keep it going, usually you're going to be calculating the kinetic friction. But last but not least, what if the object wasn't going with a constant velocity? In the last part, you're told that the object is actually accelerating to the right. So the object is actually accelerating, going faster and faster to the right. If it's accelerating to the right, how is the applied force forward going to have to compare to the force of kinetic friction? Alex, how would that applied force forward compare to the sliding friction force? If it's accelerating,
Should be greater.
how is that? It's going to be greater, yes?
What if it's,
So,
what if it's slowing down then? Like,
if it's slowing
It's gonna
down,
be less.
how would the applied force?
okay.
It would be less.
Got you. I got you.
But in this case, it's speeding up, so it's going to be greater. So I go to law number 2 from a man named New, which states that the net force is equal to the mass times the acceleration. And Andrea, in this case, I need an expression for the net force in terms of the horizontal forces up here. So what's it going to be for the net force in this case in terms of the horizontal forces acting on the object?
FF.
Well, which one's bigger, FA or FFK?
FA.
FA. And we always want to set it up so it's going to be positive here. So what would be the expression for the net force?
FA minus FFK equals M times A.
And we're trying to find what the new applied force would have to be. But it doesn't matter whether it's going with a constant velocity or accelerating. Once it's sliding, the sliding friction force always stays the same. So how much is that FFK going to be?
20 newtons.
20 newtons. And what's the mass of that object?
5 kilograms.
5 kilograms. And the problem stipulates that that object will be accelerating 2 meters per second squared.
Where do you see that?
It says that in the other side.
Oh.
Yeah, it's given.
I was gonna say.
Yeah.
Come on, Josh. Do better than that. Do better than that.
Me.
John, you want this?
No. Actually, I got this.
So FA minus 20 newtons equals 10 newtons. So what does that applied force have to be?
30 newtons.
So the applied force would be 30 newtons when the object is accelerating forward.
From a man named Bill.
So that's part C.
I see it.
One more sample problem.
Totally awesome.
A cup of coffee is sitting on a table in an airplane flying at a constant altitude and velocity. The coefficient of static friction between the cup and the table is 0.30.
That's all good.
That's mu sub s. It's 0.3. What is the maximum acceleration that the plane can have without the cup sliding backwards on the table?
Do they give you the weight or the mass?
No.
Oh, that sounds bad.
So guess what ends up happening with that?
What happens?
It ends up canceling out, not being a factor.
Wait, could you go back to?
What do you mean by that? Because
It turns out that you can let the mass of that cup be any value you want,
It will be factor.
and if it has the same mu, the same texture number,
the acceleration is
the plane's acceleration would be the same. It doesn't matter on what the mass is.
So why did it
Oh,
matter
so
in
you
this
can
problem?
just set a value for the mass and just solve
You
it.
could set a value for the mass, or more sophisticatedly, just call it m and watch how it cancels out. So, we were looking like here is a person. They're sitting at the tray. There's the tray. On the back of the seat, the person in front of them. Another person sitting up here. Whatever. And here's the coffee cup. And everyone's always happy when they're flying, going on vacation.
Monster throwing off.
And the only thing we're told is that, hey, the mu sub s between the bottom of the coffee cup and the table is 0.30.
So it can't go higher.
And the question is, how fast can that plane accelerate
Less than.
before that coffee cup will start to slide back on the table? What's the maximum acceleration?
Oh, I see. That makes sense now.
So, what we're going to do is draw a free body diagram for that cup. And of course, the cup has its weight force holding it down. That's sub g. And the table underneath it is holding it up. The normal force. And those two cancel each other out. Now, if the plane starts to accelerate forward, faster and faster velocity, the force that's actually going to have to bring the cup to that faster speed, the forward force that's going to have to make that cup speed up as well, is actually, believe it or not, a static friction force.
Why?
What other force is going to make the cup start to speed up forward so that it keeps up with the plane speed?
Oh, it pulls it forward from
Oh,
underneath
okay.
it. That's cool. That's cool.
What?
When the plane starts to go faster and faster and faster this way,
Yeah.
But that can't be.
the table underneath it
It's pulling.
is going to be anchored to the plane. It's going to be going faster and faster
Yeah.
this way.
So is the cup
So-
going that fast?
What's going to bring the cup forward going faster and faster this way?
The static friction of
The
the tray.
static friction force between the cup and the tray. If that cup was on a sheet of perfectly smooth ice
It wouldn't go.
and the plane start going faster,
There's back.
then guess what the cup would do?
It was still on that poor lady's lap.
Yeah, because it's not that it actually would go backwards, but what would it actually do?
It stands still.
Huh?
It stands still.
Not because remember what's the plane doing the whole time though? It's moving. So let's say the plane's moving at like 500 miles per hour. Well, now if all of a sudden the plane starts accelerating and goes like 600 miles per hour, what's the coffee cup going to want to keep doing?
Going at 500.
It's going to want to keep going 500 miles per hour. So it's not that it's actually going backwards. It's that the whole plane goes faster forward and the cup wants to just keep doing what it was doing.
It's going too slow.
It's going too slow. But what's the one force that will keep the cup coming forward?
Static.
The static friction force right there.
Okay, I
The
get it.
static friction force.
Oh my god.
Wow, that was mind-boggling.
Haven't heard that.
The people who aren't here, I want to see if they understand this.
So
Fucking right up buzzer.
if we apply Newton's second law to this, we know that the net force acting on the cup equals the mass times the acceleration. But what's going to be providing the forward net force on the cup? This is so weird because usually we think of friction force as the thing that slows down the motion, but in this case it's actually the force that's causing the acceleration. FFS equals MA. And if we want to push it to the limit, if we want to see how fast that plane can accelerate, well, we're going to have to reach an acceleration where that static friction force becomes a max. But what is the maximum static friction force always equal to?
Mu times the normal force.
Yes, mu sub s times the normal force.
2030.
Oh, is the normal force and the mass gonna cancel?
Well, the normal force is equal to the weight force, so mu sub s times the normal force can be replaced with mu sub s times the weight force. I just changed the normal force into the weight force here. But what's another expression for the weight force?
MG.
mg. Nice job, Robert. And voila, it wouldn't matter what mass you had, they cancel out. So it's just going to be 0.30 times acceleration due to gravity, 10 meters per second squared equals the acceleration. So the acceleration that the plane can have is 3 meters per second squared. And if the plane accelerates any faster than that, then there won't be enough static friction force to hold the cup on the table.
That's not a lot. Makes me a little nervous.
So
about when
3
I'm playing with
newtons.
hot cup of coffee.
3 newtons?
That's not on a flat surface though. You have like a ridge. You have a ridge for it.
This
And
was
have like a
something
hole.
to me. Why did mass not matter in this problem, but it did matter in the first problem?
Sometimes the tray suckers.
What's that?
Why does the
Why
cup
did
stay still
mass
until
matter
like
in the
having
second
to
problem?
Why not stay still? Why does the cup move forward? If it were ice,
Why did mass not matter in the first problem?
so
If it was
Are we
if
done?
the tabletop was icy
yeah.
and the plane started going faster and the chair connected to the plane and the table's connected to the chair, the table is going to start going faster.
Got it, yeah. And the cup, since it wants to stay at rest, it's going to swag.
Not that it's staying at rest. It would be staying at its original speed.
Got it.
It's going 500 miles per hour to begin with.
Yeah.
I hate nice.
So the cup that wants to stay at its
Right. Right.